Okay, so now we're going to look at logistic regression, and the first thing that you have to know about logistic regression is that it is a non-linear classifier. Okay, so we use it for data sets that don't have a linear distribution, and for this I will give you a very simple example. Okay, so let's assume that we have this problem in which we detect as a feature the age of the person, and what we want to classify is whether he watches The Walking Dead or not. Okay, so we may assume in the first observation that people that are behind these ages don't see this area, but the people that are up above this age, then they see this area. Okay, so you may think as making a classifier for this just using a linear regression, in that it is going to have this kind of distribution, and based on this it will be very easy to classify, because we just have to do something like this and then set a threshold C as we can see here. Okay, but that is not the case in this kind of problems, because as you can see, this is what really may happen in a distribution that looks like this, and again we have the age as a feature, and we have a distribution that is not linear. Okay, so if we try to fit any linear regression or polynomial regression, it's going to be pretty hard to make the classification. Okay, so it's not going to work at all. But what if we add a classifier that is able to solve this kind of problem? Okay, and for that reason we have this data set right over here that you can see, and for example we want to classify whether a person has tuberculosis or not based on on his diagnostic of a Nielsen sputum smear. Okay, so the distribution may look like this, and as you can see right over here, the red dots explain this, that the person lays beyond this. Oh crap, stupid computer. Okay, so as you can see, we can solve this problem just by taking a distribution that looks like this, that is non-linear, and making a hyperplane or some sort of function that divides the function by this. Okay, so we classify this as being 1, being this as being 0. Okay, based on this feature that you can see right over here. So that is the point with this logistic regression. So I'm just going to make everything faster than in the previous video. So we will go straight to the parts that compose a logistic regression. Okay, so we'll start with the hypothesis. In the hypothesis, we can see that it's not the same as in the previous one. It's not a linear or polynomial sum of weights and variables that you have, but you have now a function that transforms a number into a probability. Okay, so I'm going to draw this better. This is what we call the sigmoid function, and this sigmoid function, what it does is that it takes a number and converts it into a probability. Okay, so the look of this curve is like this. And so whenever we have values that are 4.6 or greater, the curve usually reports 1, and when we have values that are minus 4.6 or less, then we have a value of 0. Okay, and we can achieve that just by using this 1 over 1 plus e to the minus theta, where theta in this case might be equal to theta transpose times x. Okay, so we can model now this kind of classifier using this hypothesis. Now we just go straight to the cost function. The cost function is kind of more complicated than in the previous one, and it's basically the one that you can see over here. Okay, so it's minus y of I times the logarithm of our hypothesis minus 1 minus y of I times the logarithm of 1 minus our hypothesis, plus the regularization term that we have seen before, which has to be in all the cost functions that we're going to see. So how do we model this equation from right over here? It's pretty simple if we use a function in parts. So we say whenever the level we want it to be y that is equal to 1, we're going to use this function, okay, minus the logarithm of the hypothesis. And how does that work? It works based on a plot that looks like this. While in the y-axis we have the cost of the function, and in the x-axis we have the not the hypothesis but the theta transpose times dx, okay? The features times the data series that we have. So whenever we want the level to be y that is equal to 1, we want to have a very low cost, and whenever the level is equal to 0, we want to have a very high cost. So for this, we just use minus the logarithm of the hypothesis, okay? And actually, we're going to make this h of theta of x. So we can use this function from right over here. We just invert the logarithm in order to obtain something like this. And the same happens whenever we want a level that is y that is equal to 0. In this case, we want a very high cost whenever y is equal to 1, and we want a very low cost whenever the level is equal to 0. Okay, so this means that the theta transpose times dx is much less than 1. And it means that it has to be, we need to penalize the algorithm so that the theta parameters move to this way. So for this, we just use this function. We invert the logarithm, and then remember that inverting the logarithm is going to give us something like this, but we want to get to something like this. So what we do is that we invert the hypothesis, and inverting the hypothesis will give us something like this. And then what we want is to move this one step into the feature of x, and for that we just add +1, and then we have a function that looks like this. Having a function that looks like this allows us to model the problem and penalize the algorithm whenever y is equal to 0. And that's the easy part with the crap. That is the easy part with the. Okay. I'll just ignore that. Okay, so that's. Okay, now the third part of the algorithm. The third part of the algorithm is the learning algorithm, and this is basically the batch gradient descent. And this algorithm works as we have seen before. We update our parameters theta by adding a learning rate alpha and computing the derivative of the cost function. Okay, so the derivative of the cost function is not that simple as before, and for this I have made the derivative by myself, and we'll see to take this step by step. Okay, so the first thing that we have to do, and that is useful, is to take the derivative of our hypothesis. Okay, so remember that our hypothesis is sigma of theta transpose times x. Okay, so in order to derivate that, we just square the denominator, and then we compute the derivative of the numerator, and that is minus 1 times e to the minus theta transpose times x times minus 1 because of the chain rule, taking the derivative of this, and what we have in the end is plus e to the minus theta transpose times x over 1 plus e to the minus theta squared. Okay, so we can, in order to make this easier, we're going to use theta, that is going to be equal to theta transpose times x, and the next part is that we're going to divide this into two multiplications. Okay, so we're going to have the first part that looks like this and the second part that looks like this. Okay, now remember, this is theta transpose times x. This is the sigmoid function in the very basic form, and what we can do right over here is that we add +1 and we subtract -1. Okay, and from this remember that we had this, and we can do a very similar trick. So what we do is that we keep with having the sigmoid function, and the next thing that we do is that we separate this -1 from right over here over the 1 plus e to the minus theta, and this is going to be another sigmoid function in the basic form. And the other thing that we're going to take is this +1 with this e to the minus theta with this e1 over this with this and with this, and we're going to get to this. Okay, and so this is equals to 1. So at the end we just have this of theta over 1, which is this from right over here, minus this from right over here. Okay, And so based on that, we can now compute the derivative of the cost function. Remember that the derivative of the logarithm is 1 over h of theta sub x, and that's going to be times what it is inside, and what is inside is the hypothesis. So taking the derivative of the hypothesis is what we have just calculated, and that is the sigmoid times 1 minus the sigmoid. And the next thing that we have is that we need to derive what is inside of the hypothesis. Okay, so this is theta transpose times x, the derivative, which is obviously equal to x sub j with respect to some theta sub j. And the next part is kind of the same. We just copy the 1 minus y, and it's 1 over h 1 over 1 minus the hypothesis times the same result that we have seen over here, because the 1 gets the derivative to be 0, but with a minus sign due to this minus 1 right over here, and it's multiplied times x sub j. Okay, so now we just can take this with this, and what we obtain looks like this. Okay, we just have minus y of I, 1 minus the sigmoid function times the x sub j, the second part 1 minus y sub I, the negative sign, x sub j, and the sigmoid function. So what we do is that we factorize these x sub j's, and we put them right over here. Okay, so now what we do is simple multiplications. This with this is going to give us this, the minus y with this is going to give us this right over here, and 1 times remember this minus 1 is going to become plus 1 because of this, and 1 times this theta, and this sigmoid function of the hypothesis is going to give us this, and this times this is going to give us minus the sign of this, because this is negative and this has become positive, and this is the factorized result. So, and the result, as you can see, is that we can take down these two, and I'm going to make this clear. Okay, so what we obtain is 1 over 2 times m times the summation from I that equals 1 until m of h sub theta of x sub I minus y of I times x sub j, and of course the derivative of the regularized term, which is lambda over m times theta sub j. Okay, and this we can use this. Okay, until n, and this is the result, and this is the derivative. Now what's interesting about this is that this is very similar to the linear regression derivative. Actually it's the same as the linear regression derivative, but we have a different cost. Okay, but in terms of this is the same, so we can compute the batch gradient descent very easy using the same. Okay, so now we just work with the code. The first thing that we do is that we need to import all the libraries that we will require for this problem. Then we're going to create the main function, and the first thing that we're going to do is to read the dataset. I'm using an old dataset. I'm using one that I have taken from Andrew Ng's course at Coursera, and you can take that, but take the course as well. It's very recommended to start working with machine learning. Besides that, you're going to be using Octave, so it's way more easy than using Python. So the next thing, as in the previous video, we also need to normalize the data. Remember not to normalize the data whenever the data is already normalized. I mean, it's in a range from 0 to 1. Then we're going to define the parameters. And the parameters are simple, just a number of features that we have. Remember that the bias term has to be added as well. And next, we're splitting the dataset. To split the dataset, it's really recommended to use the train test split function from sklearn. It's pretty, it's very quick to use, and as you can see, it's very easy instead of doing your own randomized function. And the next thing is that we define the gradients. Now the gradients are the derivative of the cost function. And for this, as we have seen in detail in the first part of the video, the derivative at the end becomes something very easy to compute. Just remember to add the Sigmoid function, which is going to allow us to transform from our numbers to probabilities, and that is basically the basic concept of our of our hypothesis. Also remember not to penalize the first theta of the bias term. Then we just update our thetas using the gradients so that we can minimize our cost function. And once we have the thetas, we're able to predict new outcomes. For that, remember that you have to use the sigmoid function and the matrix multiplication, and also there's one more step. You have to look for the values that are over 0.5 in order to declare them as 1, and the values that are lower than 0.5 need to be 0. That is not something that the sigmoid function will do. So we just use an sklearn classifier in order to prove that our results are good. It's very easy to use the sklearn model. It's just 2 lines of code. The problem is that you learn almost nothing to just use it. But it is still very important to do, because as you will see with this dataset, the dataset needs a circle. I mean, it needs a circular function in order to classify correctly the data, and for that you must do some manipulation in the data, okay? And the manipulation in the data, I mean, it's adding new in data science they are called covariates, so you must add those covariates, and those covariates are going to be your new features that you're going to use in order to make your classifier more nonlinear and able to detect the data. In this case, we're just using a known classifier, but doesn't have the correct features. So as you will see, we will get similar results than the sklearn model, but more analysis is required. But still, you will see that we will be able to classify the data very well. So a few errors that we have to fix. The code is on GitHub and it's the working code, so there is no need to worry about these problems that I'm having right now. Just go to the GitHub and there you will have the corrected code. So after debugging a little bit, I decided to add a few functions. So here you have the cost function, and it is learning, and after a few iterations it converges, so it stays there. So then we have the classifiers, each of them, and in the final part, what I was talking about here are the different classifiers with the label market. So here it is, a simple logistic regression classifier.